Okay, in chapter 7, we're going to talk about the normal distribution. Before we talk about normal distribution, let's talk about continuous random variables. Now, we talked about continuous variables again back in earlier chapters, the first week of class. So a continuous random variable is just like a continuous variable, except the addition of the word random. That means we don't know the outcome of the experiment ahead of time. And many examples follow a continuous random variable. So for example, everything that is pretty much measured, such as time, distance, waiting times, or how fast you drive, anything that has the potential to lie inside an interval where it can assume the variable outcome can assume any values on the real number 9. Okay, so that would be the indication that the variable is continuous. So remember, as long as it can assume any values on a real number line, then it can be continuous. This is different from discrete. Remember, in the case of a discrete, there were gaps between numbers, so the values cannot be contained inside an interval. They have to be separated, and there has to be gaps between numbers. So in this section, or in this chapter, actually, we're going to talk about now continuous random variables. Now, the probability distribution of a continuous random variable will also be continuous, and that is what we're looking at in this chapter. We're going to look at one of the most well-known continuous probability distributions, namely the normal distribution. Now the word normal here, the normal curve is actually a symmetric bell-shaped curve, as you can see here on my drawing. This is what we call a normal curve. Now, if we were able to find the area under this curve, then we would find out that the area is 1, which makes this a valid probability distribution. So the curve, again, it looks the way it does, and the center of the distribution is where the mean of the population is, mu. This is random variable x. And the distance from the center to this specific point that I have circled is where the standard deviation is. We can do that with normal distribution because the way it works out. Now that point that I have circled, I have kind of a blow up of that segment of that circle right in here. And what I'm showing here is the fact that if you look at these arrows, you see I have these down arrows, and then we have these up arrows. These arrows reference to the concavity or the bending of the curve. Okay, so coming from in this direction, it looks like the curve is bending downward, and going the other direction, it's bending upwards. So the point where these up and down arrows come together, the point where they meet, which is right in here, that point is called a point of inflection, where the concavity or the curvature of the curve actually changes. Okay, so that's what those are. And let me just put one of these back on there. There we go. Okay. So I just want to point that out. We're not going to do anything specific with this point. It's just a reference for us. It's a place we can actually show on the curve. Now, for those that are interested, this is the functional form of that curve. Pretty interesting function. It's got a bunch of constants. Here, 2 is a constant, pi is a constant, e is a constant, a half is a constant, and the square here. These are all this. They have to be the way they are. E, you may note that E is the base of the natural log, which is 2.718 ... It's an irrational number. And pi is the familiar 3.14. It's the familiar 3.14. Again, rounded, of course. That is also an irrational number. X is the value of the random variable that theoretically can range from -infinity to infinity, and mu is the mean, or the center. Ranges from -infinity to infinity also. Sigma in the denominator here, that's the standard deviation, which we always take it to be positive. Again, you don't need to worry about this function because we're not going to plug in any numbers into it. This is just general information. Now, one thing that is important is that, well, how do I find probabilities under this curve, right? Well, in order to find probabilities, we need to find the area. Okay, so that's what I have here. The probability is the area under the curve, right down there. Okay, so in order to find probabilities, we got to find areas. Now, in order to find area, I need to either do it using integral calculus, because the region under the curve is not like a rectangle, a circle, or a triangle, something that I know. So we need to use calculus to do it, or we use software. Being in the course that we're going to use Megastat software to do this. And this is the three-dimensional version of the curve. This is when we have two random variables that are jointly normal, and z here is going to be again the outcome, the value of the random variable. That's what the z is here, the third axis, if you will. That would be this third axis. Okay, and this is, of course, this is kind of like where the x is, and this is kind of where the y is. Okay, just want to point this out. That's ideal go to multivariable cases where we have more than one variable. Now, every normal distribution, the ones we look at, have what we call two parameters. The parameters are the values we need to know in order to be able to find the values under the curve. Okay, so the parameters of the normal distribution are the mean and deviation, mu and sigma. So for example, here I have an example. I have a normal distribution. The mean is 100 and deviation 5. So that's what this means. There are different normal distributions, by the way. If you change the mean, change the deviation, you get a different looking normal distribution. They're all going to be symmetric and bell-shaped, but the specifics of each of them may change, as you will see in many examples that are coming up. Now, if you look at a very special normal distribution, it's called standard normal distribution. The standard normal distribution, this one, standard normal distribution, is a distribution whose mean is 0. The mean has to be exactly 0. Deviation has to be exactly 1. Any other combination is not standard normal. Okay. Now, since we're using Megastat, for us really standard normal is just another distribution. But if we were to do things by hand, because the values under these normal distributions have to be determined either again by software, integral calculus, or in a lot of cases we have tables that are provided by the authors in the book. Well, we cannot have a table for every different normal distribution out there. It's impossible. So there is a table of only one normal distribution, and that's the standard normal distribution that every statistics textbook has. So that table has to be for the mean 0, deviation 1. And then there's a process called the standardization, where we can transform non-standard normal distributions, that means the ones that don't have mean 0, deviation 1, into a standard normal distribution, so we can just use that table. That's the only advantage of that table. So, but because we're not going to do that, I won't even bother going to the table with you. So here's what the standard normal distribution looks like. There you go, 0, 1. Mean 0, deviation 1. And also note, by the way, due to the symmetry of the distribution, mean, median, and the mode are all the same in a normal distribution. All three of those are the same. So if a variable follows a normal distribution, then it doesn't matter which measure of central tendency we use. Now here I'm showing you about that process that I mentioned, the standardization process I mentioned earlier. So what I have is a non-standard normal distribution. The one on the left is the one with the mean 100 and deviation of 0.5. let me see. Yeah. Oh, okay. No, I'm sorry. The one on the right, I'm looking at this one. Okay, that one. That one is a normal distribution. Let me write the parameters of this one. This is a normal whose mean is 100 and deviation is 1/2. That's what that is. And through this process of a standardization, I'm standardizing it into a normal 0, 1. So the distribution on the left is normal 0, 1. And a simple transformation that takes place right in here. You have this formula right in here. That is x minus mu over sigma. So in this formula, this transformation, if you will, we subtract the mean divided by deviation. So the effect of x minus mu is to relocate the center of the distribution from what it was 100 to where it's at now 0. And the effect of dividing by sigma is to rescale it. So the deviation used to be 1/2, right in here. The deviation is 1/2. At this point, the deviation is 1. Okay, with this process. And what I'm doing is actually this also. So this observation, 100.5, that one. I'm actually tracking this one value, 100.5. And once I do 100.5 minus 100 divided by 0.5, that's just going to be, this is right in here. Let me fix this up. That's 100.5. 100.5. You subtract the mean of 100 divided by deviation of 0.5, and that will standardize this variable, the value of the variable, into a z-score of 1. So if you look at both ways, let's say a score of 100.5 in the right distribution, because deviation is 0.5, so that score is 1 deviation above the mean, correct? 1 deviation is 0.5, the score is 100.5, so that means the score of 100.5 is 1 deviation above the mean. Once I standardized it, notice it's still 1 deviation above. Z equal 1 means 1 deviation above the mean. So again, the reason we mention this is for those that use the table, but we don't in this course. The other interesting fact about the normal distribution is what we call the empirical rule here. So what we're looking at now is the empirical rule. The word empirical means based on real data. So what this empirical rule actually says is the following, is that in any mound-shaped distribution, normal distribution, the interval 1 deviation, plus or minus 1 deviation, that's this line, contains almost 68% of all scores. Okay. And the interval that is, let me fix this up here. Hold on. Sorry. Okay. So I was just going to show you. I'm looking at this right here. Okay. So 1 deviation above or below that total interval contains 68% of all scores. 2 deviations above and below contains 95.4%, and 3 deviation covers almost all of the scores. And that is why the distribution is used so often, because only 3 deviation, 3 sigmas, that would be 6 sigma total from low to high, covers almost all of the scores are in there. So there's not much going on outside of those intervals as far as the amount of data that's contained. Okay. Now, again, I just want to emphasize that we're going to use megastat to find the area under the normal curve. And from judging from the homeworks you've been turning in, it looks like all of you are working with megastat. So I'm just going to show you examples today from now on megastat. Okay. Not in Minitab, unless you ask me to. So here are the examples that I actually ran in megastat, and I'll show you where these numbers come from in a moment. So what I've done is I made up again that normal distribution where the mean is 100 and deviation is 5, and we want to find probabilities of those events. probability the values less than or equal 87, less than 87, equal 87, between 96 107, and greater than 111. So these numbers, we're going to get them all from Megastat. Now, one thing to note, I want to point this one out, okay? And that is for the case here. For any continuous probability distribution, probability of exactly equal to a number is going to be 0. We don't need a software for that. And the reason for it is because when you try to find the area under the curve, let's say here's my normal distribution, okay, and suppose this is x, here's the center 100, and here's 87, let's say. I want to find the area of that line. Now I'm making the line thick so you can see it, but remember, a line can be as thin as a strand of hair. But the point being, I want to find the area of that line. So under the curve, well, the line does not have an area. Okay, so because it doesn't have an area, so I cannot, there you go, see, I made that thinner now. So the area of a line is 0. So that would be the geometric justification for the 0. But this implication is what I'm interested in. Remember, for any continuous probability distribution, probability of exact values are zeros. Okay, so for that reason, if you look at the answer to part 1 and part 2, they're exactly the same, these two numbers, right? Because the difference is in the second part, I remove the equal sign. And because probability of exactly equal in part 3 is 0, therefore those two first probabilities will be the same. And I'll show you right in a few moments how to do this in Megastat. For this example, the probability that between 96 and 107, again, whether you include equal sign right here, there you go, you can include it, or you can actually remove them. There you go, here, I removed it now. See, it doesn't make a difference. The probability will be the same. So probability of between 96, 107, inclusive or exclusive, would be the same. Now this was not the case with discrete probability distribution. It makes a big difference whether you include or exclude the values. And finally, probability of x greater than 111 is 0.0139. Okay, and okay, so let me pause here. I'm going to go and bring up my Megastat, and we're going to do these in Megastat and get these numbers. And again, you have the numbers, so we're going to get these off of Megastat in a moment. Alright, so now I have Megastat in front of me. I've already loaded the add-ins, and we know where to find it. So when I go to add-ins and I look at Megastat here, let me click on Megastat. So we want to find the area under normal distribution. So we're going down to probability. And then we go to, there are two ways you can go to normal distribution. Notice here, by the way, these are well-known distributions we worked with in this course. All four of them we worked with. We have normal, T, F, and chi, not chi. I know it's chi, but we read it as chi, Ki, chi-square distribution. You can get to them individually this way, or you can click on continuous distributions. If I do, you see all four of them this way. Now, the way this is right now, the default is normal. It's got 1, 2, 3 inputs with limited options to do anything. So let me X this out. I rather go to it this way. I go to probability and I go directly to a normal distribution. Check this out. Now I have more options. So what I want to do is I want to calculate P, calculate probability given a Z. Notice it says Z score, but don't worry, we can actually put X values. The reason it says Z is because default means 0, deviation 1. Remember the standard normal I told you about. The moment you change this 0, 1 to something else, note this Z and the Z here are going to turn into an X. So let me do that. In our example, the mean was 100, correct? So I'm going to put 100 in this example. See, as soon as I just put 1, not even 100, the z became x here, and it became x here. So that's just noteworthy. Mean is 100, and deviation is 5. There you go. Okay, the x value is the value of the random variable. In my first example is 87. And down here, the shading, it shades whether it's a lower tail or upper tail. Now for two tail, it doesn't have option here. I don't know why. But it has option to give you the upper portion under the distribution, or the lower portion. Well, less than 87 means lower. For less than or equal, you go lower. For greater than or equal, you go upper. And then don't worry about these. You can leave them alone. You can show the axis. Keep these defaults. Now, for choices, I'm just going to go transparent. You can go solid color. You can go pattern. You can put no shading at all. I like to go transparent. Okay. But you can play with this and see how it turns out. So there you go. That's all you do. Input the value of x, mean, deviation. These are the parameters of the distribution. And then whether you want lower or upper, below that or greater than that. Let's hit OK. And you're going to see a normal distribution here drawn. And of course, let me reduce the size of it. And there you have it. See how nicely drawn? This is the normal distribution. Okay, so down below here, it does a transformation. It will standardize at 87. It says, okay, well, if you want a z-score, this is what a z-score looks like. You see that? It transformed it into the distribution into a z-score. You see that? This is a standard normal distribution, mean 0, deviation 1. So it standardized it. And the probability is going to be 0.047 lower. That is the area to the left. And it's going to be 0.9953 for the upper. That's the area to the right of it. And that's how I got my first number. For the second part, with the probability is just less than 87, it's going to be exactly the same. So I'm not going to run that. And equals 87, well, that didn't even give me an option for equal to, so that's just common knowledge that part 3 probability will be 0. Now, let's do between 96 and 107. So here's how you do between. Go make a stat, probability, and go normal. Okay. Now, notice since we ran this already, there's this thing that appeared here, it says overlay. Make sure you uncheck that. Okay, so this time between 96 and 107, I'm going to go 107, the higher number first. Same parameters. Okay. Oh, and the axis label here, see, is z or x. Let's go x. That's how you can prevent it from standardizing it. Okay. So this way it actually shows me mean 100, deviation 5 distribution, not a standard normal. And so we want to do less than 107. Okay, and hit OK. Less than 107, and there you go. Remember, this is our previous run. This is the new one right in here. And note, if you look down here, see, this is now x. It did not turn it into a z-score. So this is what that normal distribution looks like. The mean of 100, deviation 5. And the default tick marks are in units of standard deviation. So you see 107 is between 1 and 2 deviation. If you standardize it, there is a z-score. It's about 1.4 deviation above. That's what that score is. Now, the area to the left of that is 91, 92. Okay, now we want between 96 and 107. So everything that's below 96 right in here, below 96 is extra. It's the excess. We don't need it. So I'm going to go make a stat, probability, normal. This time, make sure it's overlaid. So for if you want to find probability between two scores, you keep that overlay, okay? And then change this now to 96. Okay, everything is the same. Now change this to solid color, otherwise it's going to be confusion. Solid color, and because it's overlaid, you're going to see a shaded area. Okay, right in here you're going to see a shaded region in here. Let's hit OK. And there you go. You see that? This is the extra region that we didn't need. So that's the part we want to subtract out. So what do I need to do? In order to find the area that we need, I'm going to actually subtract. Let's see. Let me do this. I'm going to see if this works. Ooh, that's too large. Hold on. So we can get, again, the area by subtraction. So if I subtract 0.2119 from 0.9192, I will get the 0.7075 that I had in my notebook. So that's how you get the area between. Now suppose I want to do the area above 111. That's the last part of that example. Go make a stat, probability, normal. And this time you change your x to 111, and the upper, that would be the the right tail, and remove the overlay. We don't need the overlay. This is a whole separate problem. So we get a different normal distribution now. Not different in shape, it's just now the shading is going to be different because this is a different probability statement. So there you go. 111. If you just visually look at the graph, that's 1, 2, between 2 and 3 deviation, closer to 2 deviation, a little over 2 deviation above the mean. And this is what the z-score says, this 2.2 deviation above the mean. And the area to the right, that would be the upper. We wanted the upper. It's going to be 0.0139. So that's the answer to that exercise, or that example that I made up. Okay, so it's pretty easy to do. We can do, therefore, upper does right tail, lower does the area to the left. We can do left tail if you wanted to. And we just did the example of between. There you go. This is how you do between. For the between, you do a higher number minus the lower number, the area for those. Okay, so let me go back to our note, and we're going to look at actually a word problem now. Okay, one thing, by the way, before we actually look at a word problem, I want to point this out, and we can verify a couple of these. I'll leave the rest of these for you to verify. Is this notation z subscript with alpha, z sub alpha? Okay, so what the z sub alpha means is this. This is a standard normal distribution. Variable is z. The z here is a z-score. And subscript alpha, alpha is an area, okay, to the right. And it's always to the right. So I want to find a z-score, so the area to the right measures alpha. So for example, z.1 means a z-score, so the area to the right is 0.1. z05, what z-score has area to the right? 0.05. This one, what z-score has area to the right? 0.025, and so on. So that's what these z-scores are. So let's verify a couple of these. For example, I'm going to do z of 025 and z of 01. 025 and 01. We're going to do this in Megastat. Okay, a z of 025 and z of 01. You can verify the rest. Okay, so what I'm going to do now, I'm going to go to Megastat. Let me scroll down. These are from previous run. Okay, Megastat. And go to probability, normal distribution. Now this time, we actually want to find the z-score, right? So because it's a z, I'm going to first change mean to 0, deviation to 1, and notice this x is going to become a z. There you go. So now the software knows, okay, he's working with a z-score. Now, before we actually put in a value of random variable, we put a value for the random variable, and we found the probability. This time we're doing just the opposite. You see this? So we're going to actually calculate a z for a given p, for a given probability. That's what I want to do. And look at the numbers, by the way. Look at those. The ones that I have are already there. So let's do, I said we want to do the 0.025. This is 0.0, and you can type in your own number, like probability 0.4532. There you go, whatever you want. I want to find the area to the right to be 0.025. Okay. And upper, make sure this is upper because we want the area to the right. And that's all you got to do. And here it doesn't matter if you say X or Z because things are going to be, this is going to be a Z anyway. So I'm just going to leave these alone. And let's go transparent. Okay. And there you have it. And here you have it. Because this is the Z area to upper in boldface. That's the one I had. Let me enlarge this so you can see these numbers a little easier. There you go. You see this 0.025? That's the number I put in. The Z that goes with that is 1.96. And this is what it looks like under the distribution. See, of 1.96, the area to the right, this shaded region on the right is 0.25. Okay, so that's what that is. Now let's verify the 0.01. That's the other one I want to do. So I go probability, normal, and it's already one of those. Yeah, might as well use it. 0.01 and hit OK. Oh, overlay, we don't want to overlay. Okay. And this time you're going to actually see a bigger number, right? Because we have a smaller area on the right. The Z-score increases to offset the smaller area, right? So there you go. The area to the right, 0.01, the Z at that is 2.33. 2.33, and that's what that score is. Now, if you want more decimal beyond, let me enlarge this. If you want beyond 2.33, if you look up here, you see that? That's really what the number is, carried to 16 digits or so. 2.326, that's the one I had in my note. So 2.33 is just a rounded value. That's what that is. And I think if you click on this and if you go to home, and there you go, let's see. Oops, the other way. See, you can add more decimal. The number actually shows with more decimal accuracy. So you can adjust your decimal points here in Excel this way. So again, just want to point this out. The reason I did is because next week, when we talk about confidence intervals, we're going to be using these scores in our formulas, although we do this in the software. But anyway, just want to point that out for you, what the Z with the subscript meant. Okay, so now we verified a couple of these Z subscripted Z's. So you can verify the rest if you like to. So now let's take a look at an exercise here. We're going to do this exercise again in Megastat, but first we're going to actually write down each of these using probability notation. Okay, so in this exercise, and I believe this is from your textbook, so it's something that's come from your textbook. The problem reads: the annual commission earned by sales representative of Machine Products Inc., a manufacturer of light machinery, follow the normal probability distribution. The mean yearly amount earned is $40,000 and the deviation is 5,000. Okay, so we're just going to put this information down. The mean, mu, is 40,000 and the deviation is 5,000, which is rather large relative to the mean. Okay, in part A, what percent, and the word percent in this line of work for us, it means probability also. You can translate it into probabilities. What percent of sales reps earn more than $42,000 a year? So that would be probability. So the random variable X is the amount a sales rep earns. X. We're going to call that X. More than 42,000, so it's going to be greater than 42,000. If you put the equal sign, doesn't matter, but remember, just to adhere with the correct verbiage here, more than means you don't include the equal sign. But on the probability side of things, if you did, the answer would be exactly the same. Okay, so that's for part A. And then in part B, we'll get this number from Megastat in a moment. In part B, what percent earned between 32 and 42,000? So that's going to be 32,000 and 42,000. Notice there was no mention of inclusive or exclusive. It doesn't matter. And in part C, what percent of sales rep earn between 32 and 35,000? In part C, that's probability 32,000 x between 35,000. There you go. That's going to be smaller area, so that's going to be lower probability. And in part D, the sales manager wants to award the sales rep or reps who earn the largest commission a bonus of $1,000. Good for them. He can award the bonus to 20% of the representatives. What is the cutoff between those who earn a bonus and those who do not? So the cutoff is 20%. So you want the highest, the top 20%, right, to earn the bonus. The key is that top 20% means to the right. So what we want in part D is this. We want to know probability of X, random variable X. That's what these are. Capital X represents the random variable. Got to be greater than some value of X that we want to find out in this exercise. And we want to know what this cutoff is. That's our cutoff. What is that value so that 20% lies to the right of it? Okay, so that's what we want to know. So when we go to Megastat, remember what we're going to do? We're going to, instead of putting an X, finding probability, we're going to put the probability finding the X. Okay, so we'll do that last. Now, with this, let's go to Megastat to complete this exercise. Okay, so I'm in Megastat now, and we're going to input the information that the exercise provided. I'm going to go to add-ins and Megastat, probability, normal distribution. Now in part A, we want to know probability of greater than $42,000. Make sure you calculate probability given Z, remove the overlay. You only use overlay for between, okay? So the mean was $40,000, so I need to input that value of $40,000 in here. So here's 40, there you go, $40,000. The deviation was 5,000, and there you have it. Okay, those are the parameters. Now the software knows exactly which normal distribution to plot and to work with. And the value here we want is 42,000, right? And we want greater than, so that's upper. And we're going to use X for our labels, okay, not the Z score. We get the Z score anyway in the output. I like to work with the original distribution. And we want the area upper. Oh, just to be different, let me show you the pattern here, just so you see what it looks like. And you see maybe a cross hatch or just a single hatch. Yeah, there you go. So if visually this is more appealing to you, then of course you're welcome to use patterned. But here's the answer to this exercise. Probability of 42,000 or more, that's all of this region to the right that's shaded. That area upper is 3446. Okay, 0.3446. That means better than 34%. Almost call it 35%. The Z score at that point, the score of 42,000, is 0.4 deviation. Not quite one, not even half a deviation above the mean. And it gives you, again, the mean is 40, deviation 5,000. It just echoes what we input into it. The X value we put in was 42,000. So right down here, this is informative. And there is a nicely drawn distribution. And you can, by the way, copy and paste these. Like if you select it, see I left click once and then right click, you can copy and paste it into a Word document, what have you. And adjust it, play around with it, and so on and so forth. Okay, so there's that exercise. Next, in part B, between 32 and 42,000, right? I'm going to go megastat, probability, normal. Now, remove the overlay. Now, between 32 and 42,000, so we're going to put a higher number first, 42,000, and go lower. My shading, I want to change to transparent, and hit OK. And that will generate my distribution. There you go, this one, but that's not the answer we want, right? To get between, we need to overlay another one on top of this distribution. So I go megastat, probability, and normal. Here's the overlay, checked, and change the lower number to 32,000. And make sure you change the shading. Okay, go to solid color. So that way there's a pronounced difference between the two shadings. Otherwise, visually it's confusing. And hit OK. Now you're going to see it right in here, right down here. There you go. This is the excess that we didn't want. We want between 32 and 42,000. Between those. That's this kind of bluish region. Or gray, not blue, but kind of gray, heavy gray region. So what do I need to do? I need to get the higher area at 42,000, probability of lower, that's the higher area. 6554, right? That's going to be 0.6554, and then we subtract from that 0.0548. 0548. And because you're in Excel, let me show you. You can actually do that. You don't need a calculator. I can go equal, up arrow that number, minus up arrow that number. There you go. You see that? So that's and again, if you want to use a formula, you can use a calculator. What I did is, let me show you again. I hit equal sign, and then I use up arrow on the keyboard. I went to that cell. Minus, I up arrow to the cell below it, enter, and I got that answer. So the probability is about 60%, 0.6006. With probabilities, remember, we usually round to the nearest 10,000ths. That means 4 decimals. And there you have it. Okay, if you want to round this, go to home and right here. See, I'm up here, and reducing the number of decimals to however many accuracy. There you go. 0.6006. That's what that is. Okay, now the other part was between 30. Let me scroll that. I'm doing part C now. I'm going to go add-ins, megastat, probability, normal distribution, and between 32 and 35,000. So change this to 35,000. Remove the overlay. That's the higher of the two numbers. Transparent. Get that lower number. And there, this is what I mean by lower. Get this number. Now we actually put the lower value of x. That was 32,000. We're doing part C of our exercise. Probability, normal, overlay is turned on, and we go 32,000 and change to solid and hit OK. And there you go. You see that? So 32,000, between 32 and 35,000 is this region. So I need to subtract the two numbers, right? That's 0.1587 minus 0.0548, 0548. Okay, so again, let me go down here. So I show you, I hit equal sign on the keyboard. Up arrow. Once you reach the cell, then you do minus, up arrow to that, and hit enter. There you go, 0.1039. 0.1039. and that is rounded to the nearest 10,000ths. Okay, let's do part D of this exercise. In part D of this exercise, we're given a probability area. We want to find the x. Remember, that's the one for award. So I go probability, normal, and change this to calculate x given p, uncheck overlay. Now the probability is 0.2, so go 0.2, 20%. The mean and deviation don't change, and make sure you do upper, because the upper 20% are going to get the award of $1,000, right? That's our cutoff point. And we're good. Just everything looks okay here, and hit OK. And the cutoff point ends up being $44,208.10. That's this number right in here. There you go. You see that? 44,208.10. So roughly at $44,000, that would be the cutoff. And here it is. The probability at that is going to be exactly there, 20%. Remember, once the output is done, you're in an Excel environment. You can do anything with these. You can change the fonts, you can move it, copy, use it in a formula, what have you. There you go. If you want, for example, make a bigger font, there. And the number that we're looking for is this number. So the answer to this exercise is that. And there you have it. See? $44,208.10. I looked at the graph, and there you can see clearly 20% more than that are going to earn that $1,000 bonus. Okay, so I'm going to go back to my note and input these scores. Okay, so I'm back now. Let me copy the information that we got earlier. And for part A, greater than 42,000, we found this to be 0.3446. In part B, what we ended up doing is using the overlay feature in Megastat. We subtracted the higher minus the lower area, and that number turned out to be 0.6006. In part C, we did the same thing, right? In part C, we input the higher number, 35,000. The area below that was 1587. And we subtracted the lower area of 0548 from it, and the answer to that part was 1039, about 10% probability of that. And for the cutoff, we just, again, let me just put that, we used Megastat. And the X value turned out to be $44,208 approximately dollars. So anyone that earns 44,000 or more is going to get that bonus of $1,000. Okay, so that's about all we want to do in this chapter. Hopefully everything was straightforward. You were able to follow things we did. Using the software makes our lives a lot easier. That's why these lectures go, to me anyway, they go pretty smoothly, and hopefully everybody follows, and you can now do your homework and be able to work them correctly. So with that, we're done with chapter 7, the normal probability distribution.